afternoon all. Today I will talk about how we close the loop from human demonstrations to fully autonomous robot execution via imitation learning using a pipeline built using NVIDIA Isaac Lab. Before diving deep, I will introduce myself. My name is Sanjuna Mariam Mathews. I am working as Senior Technical Lead at HCLTech. Recently, I got recognized as NVIDIA Omniverse Ambassador during NVIDIA GTC DC. I am also author of one book, Roboverse, Rose, Rose 2 and Beyond. And also I post technical content, Rose and Omniverse videos in my YouTube channel, Robotic Tips. So we all know that it is very difficult to fully program real-world tasks using rule-based programming. So what if robots could learn from human demonstration? That's the agenda of today's talk. So you can see from the pictures, these human demonstration can be a reference for the autonomous execution of robot. So as you can see in the picture, we can teleoperate the robot using different methods. We can show demonstration maybe using XR devices like Apple Vision Pro, or if we have a leader arm, follower arm, we can move the follower arm, we can move the leader arm and the follower arm will follow. And also there are other simple methods like keyboard teleoperation, IK control using keyboard teleoperation, space mouse, etc. So using this human demonstration, we are trying to teach the robots, and the robot will be able to learn how it needs to do the task in a human way. So this will be the expected output. So robots can learn faster when humans teach. So basically, we have to do automation testing using robots in a human way. Initially, we used to do it using manual test case scenarios. We had different scenarios, automated, traditional way of testing everything. Then we came to rule-based programming using robots. Now, we are trying out the ways to do it using imitation learning. So basically, each demonstration will be a data point, and imitation learning will help us to unlock complex behavior without much pain. With few demonstrations, we will be able to scale it up and then use the scaled version to train the robots so that the robot can do in a human way. So let me introduce Kinetic AI QA, which is a AI-powered quality assurance platform using cobots, which are trained using expert demonstration. So we are seeing different initial use cases for this, like consumer electronics, XR AR devices, office equipment, healthcare, IoT devices, etc. So the main differentiation is the learning itself. It will learn, cobots will learn from human demonstration, and for each product, each device, we will be able to design and fabricate a custom end effector. Basically, this will help in the end-to-end quality assurance using digital validation and physical testing. And we can integrate it to CI/CD pipeline. So whenever there is a change in dataset, the system will retrain itself, deploys the policy to the inference service, and takes the observation and decides the action based on that. So basically, this solution integrates AI-powered cobots and foundation models, which can deliver a human-like quality assurance testing. So the main advantage will be it will be able to cover touch, motion, pressure, etc. So as of now, we have started without focusing on contact now, but later we will be able to scale to that level quickly. So this was the traditional way of doing it. There are different test scenarios. So Bluetooth pairing, audio command, single tap, double tap, volume up, photo capture, video capture, dawn off. So for all these things, there was traditional way of testing all these capabilities of a smart glass. Now we are trying to do it using imitation learning, using NVIDIA Isaac Lab pipeline. Can you please play the video? So basically we can collect demonstrations from different means, and this will be the expected output. We are not in real world stage yet, but this is a automated scripting using rule-based programming. We are showcasing what is the expected output. So there are different APIs, as I already mentioned. So this is taking photo, and then there is an API to take video, and there is another API that you have already seen that was opening the hinge, and there is an API to close the hinge. So all these actions will help in different testing scenarios. So as of now, the robot is doing in its own way. We are doing a rule-based programming, but instead we need to test all these scenarios in a human way. Like a human takes the smart glass, keeps on eye, and then test all these scenarios. So we are on the track. As of now, we have one robot instead of 2 arms, but in future we will be trying it out with 2 arms. So this is the integrated device testing solution, and the demonstration that we can capture in different ways. As I already mentioned, we can have a leader and follower arm, or we can collect the demonstration in the simulation, and also we can scale it up using tools like robomimic. We can scale the dataset, and using that we will train the policy which is there in the CI/CD pipeline, and using that we will do the integration device testing, which can be later integrated with the companion apps and testing frameworks. So this is the quality assurance process framework. We will start with GROOT teleop for the demonstration capture. So, as I already mentioned, we can do it in using the real hardware and also in simulation environment. If it is real hardware, there is a web app developed by HCLTech for visualization and recording. We can use those demonstrations for training, and also we can collect the demonstration from simulation. So we can IK control using keyboard, or use space mouse, or use things like Apple Vision Pro, or there are many more methods to collect human demonstrations. And then next stage is to send to robomimic for synthetic motion generation. So there you can see the recorded trajectory, the recorded motion that will be scaled to a large data set. We can record 10 or 40 demonstrations, and we can scale it up to 1,000 demonstrations using robomimic. We are utilizing Isaac Lab for that. And then we are taking all those demonstrations to the next stage, which is we are pushing the dataset to Hugging Face, and also we can make it more realistic. We have collected the dataset from simulation, so we need to fill the sim to real gap. So we need to make all those dataset more realistic. So that for that we can use Cosmos. Using augmentation prompts, we can augment the dataset and get a richer and diverse dataset. So this is the training and inference pipeline. So with CI/CD trigger, we will fine-tune the GROOT model and the trained model that we will host in an inference server. So for NIM routing agent, for the complex tasks that need imitation learning behavior, that will trigger the GROOT inference server, will give the observations. The inference server will provide the actions required to do the particular task. For the other tasks, for the tasks which can be done using traditional methods, we can make use of Isaac rows, manipulator pipeline, and do the task. There are different frameworks. Can you please play? So I'm showing some demonstrations in Isaac Lab. So this is place smart glass. So I'm placing the smart glass that needs to be tested on the cradle. And this is the second scenario, that is capture photo. So for capturing photo, we need to press a button. So these are the two things that we have tried. So first step is recording episodes. We can record episodes. We need to record 10 to 40 demonstrations. I have recorded 10 demonstrations now. So the position of the target cradle will change. The metaglass will change. Based on all these scenarios, the robot will be able to execute the particular task. We are showing how this task can be done. So using 10 demonstrations, we have showed how this can be done. And this is using another robot, Franga robot. We are doing the same task. So you can create a pipeline, and then the same can be used for different robot embodiments. And so Franga is a cobot, as I mentioned, but Trozen is a research arm. Trozen WXA is the arm that we were demonstrating. So it's not a cobot, but to start with imitation learning, to teleoperate, it will be easier to start with research-friendly robots. So next stage is annotation. We need to mark all the subtasks. Can you please play the video? No. So in this, we are annotating the episode. All the episodes will be replayed. We need to mark each subtask. So one subtask that is involved is graphs. Second subtask is placing on the cradle. So we need to mark both. In that way, we need to annotate all the episodes. So we are telling the robot what all subtasks are there. Based on that, the data set will be annotated, and we will save that as an HTF file. So in GROOT teleop, we have recorded the motion data, motion and interaction data from the simulation scene, and have saved it as a HTF5 file. So, and then we have annotated. So this is the third stage, that is generating dataset using GROOT Mimic, where we use it for synthetic motion generation. So we have only 10 demonstrations now. That will not be enough for the robot to learn the particular task. So we are using this to scale the dataset. Can you please play the video? So we have given 10 number of trials. So in the 10 parallel simulation environments, robot is trying to do the task in a human way, how we have demonstrated. And some of the executions will fail, some of the execution will succeed. So there will be a success rate associated with this. We will be able to find it from log. So the robot is trying to do the task. Once it is done, it will exit. So that was done for only 10 execution trials. Here I am trying it with 1000 execution trials. So the success rate is 29%. If we are giving better demonstrations, success rate will be also more. So I have used keyboard for the teleoperations that I am showing it now. So with better human demonstration, success rates can be also increased. So next step is training. We are training using behavior cloning algorithm, which is available in robomimic. And once we have trained the particular task, we will be able to see it in simulation. We will be able to inference it. So this is the trial 1. So this is not teleoperation. The robot itself learn how to do the task. The robot is taking the smart glass and placing it on cradle itself. So this is the trial 1. And this is the trial 2. So with better human demonstration, we will get better output. So I am concluding. So here we are trying to use imitation learning to replace the normal manual test scenarios with a human-like way of doing the autonomous task, so that we can replace human in the loop. Instead of human, robot will be able to do in a human way. And the outcome is end-to-end autonomy solution that industries can adopt quickly. And in the image, you can see the robot that gets trained in simulation environment, and the robot at the end, we will be deploying it to real hardware. As of now, have trained in simulation. We need to do one more step before deploying to real hardware. We need more diverse data. So we can use Cosmos for that. We can make the videos more augmented, make it richer, diverser, and with real world kind of demonstrations, we will be able to train the policy better, and using that, we can deploy it to real world robot easily. Thank you. So for any question, you can reach out to me via LinkedIn. And we also have openings for Noida location. If you are interested to join our team in the Noida location, you can reach out to me. Thank you.